Dear learners, greetings from IIT Guwahati. I welcome you to this course Applied Thermodynamics. We are in the module 1, that is review of basic thermodynamics. So, in the beginning of this module, it was proposed that this module will contain 3 lectures, but however, looking at the contents, instead of 3 we are proposing 4 lectures. So, basically the first 2 lectures which I have covered, that is on thermodynamic systems and pure substance, heat and work transfer, where we focused mainly on first law of thermodynamics. Now, 2 more other lectures in this module are second law of thermodynamics, which we will be covering today, and in the next lecture we will be discussing about entropy and exergy concepts. Now, let us start this contents for the lecture 3, that is second law of thermodynamics. So, in this lecture we will touch upon the following topics: heat engine, refrigerator and heat pump, Kelvin Planck and Clausius statement. In fact, these are the 2 statements are in the form of second law of thermodynamics, and there is some concept called perpetual motion machine, and next is reversible process and irreversibility. So, this is a very important aspect as far as the second law is concerned. I will emphasize what is meant by reversible process and irreversibility, how does it affect in the for occurrence of any system or process. And lastly, we will cover the Carnot cycle and reverse Carnot cycles. So, let me give you some brief introduction about second law of thermodynamics. So, in the first law of thermodynamics, we emphasize that energy is a conserved property, and whatever change of energy that takes place or interaction that takes place, in which it takes one form of energy into other. So, there is no concept of energy creation, and while dealing with energy interaction, the first law states that it is there are 2 modes of heat transfer, one is heat and mass transfer, and that is going to happen in closed systems, but in open system in addition to heat and mass transfer, there is another interaction, that is through mass flow, where the flow energy is dumped into the system and the flow mass, that mass also carries out of the energy. And one of the most important significant property that first law introduces is the internal energy, and this internal energy is mainly for closed systems, and when you deal with open systems, the flow energy gets added into the internal energy, and we call this as enthalpy. So, this is the very basic summary of the first law, but what is the main demerit in this first law is that first law does not take into account about the occurrence of a process. So, it just makes a energy balance, or we can say it is energy audit. Whatever energy comes to the system, it goes out. So, it take a stock of it, that means entire energy that comes, that goes out. This is, but that is in fact that is not true, first of all. And second aspect is that in the first law, although it says that heat and work are 2 form of energy, but the most important point is that both have same unit, both have same quantity. If now question comes whether which is high grade and which is low grade. So, for example, if you have 10 kilojoule of heat and 10 kilojoule of work, which is at higher potential. So, these are the questions that remains unanswered, whether energy has a quality or not. And second thing is that if a process has to happen, although we can make an energy balance, but can a process occur the way the process occurs in one direction, if can it occur in a reverse direction? So, these are the questions that remains unanswered in the first law. So, because of this reason, the second law comes into picture, where the second law has answered most of these queries of these queries, and in fact, the a thermodynamics any system that is occurring in nature must satisfy both the laws. So, this is the basic inference that we will get out of second law of thermodynamics. Another important aspect that the second law gives is the concept of entropy, that gives the directionality of a process to occur. So, all these things we are going to cover one by one in this lecture and the subsequent lectures. So, just to begin with whatever I have explained, if I can consolidate them in some statements, then I can write like this. First law of thermodynamics opines that energy is a conserved property, but by satisfying the first law of thermodynamics does not ensure that process actually takes place, because there are some limitations due to irreversibility. That means, a process can occur in a certain directions, but it does not occur in a reverse direction. For example, water flows spontaneously from a uphill to downhill. So, in this process what happens? The potential energy of water at uphills gets converted to kinetic energy. So, it is flowing downhill. Now, by some means, if you want to accelerate the water, it cannot flow spontaneously uphill. That means by making an energy balance, if same energy amount, because of some limitations or restrictions, that spontaneous flow from downhill to uphill is not possible. Second example could be a running car is stopped by applying brakes. So, in this process what happens? Kinetic energy converted to the internal energy through brake shoes. Now, this if you can get back the internal energy back to the car will not move. Hot coffee eventually cools by transferring heat to the surroundings. If same amount of so this cooling process is a spontaneous process, but reverse is not happening in nature. Iron oxidizes in the air due to chemical reaction after long time, but that from once it oxidizes we cannot get the iron back. So, these are the many such occurring processes that nature that says that a process occurs in a certain directions. So, it is a spontaneous flow of energy occurrence in a certain direction. So, it gives that in the process we say, for example, when iron rusts, so there is a process of degradation of energy. So, this is typically these are the quantified through the concept of second law of thermodynamics. Energy flow is possible from higher to lower potential, but first law of thermodynamics is silent on these aspects. The fundamental science behind the second law is the fact that energy spontaneously dispenses from being localized to spread out, or if it is not hindered. So, it tries to spread out. The second law of thermodynamics asserts the two important things, qualitative as well as quantitative aspects of energy. So, it says first law talks about work and heat, they are the form of energy, but second law says that work is high grade energy and heat is low grade energy. Why? We will come back later. And so, since it is a high grade energy, the complete conversion of work to heat is possible, but reverse is not true. The second law of thermodynamics provides necessary means to determine the quality as well as degree of degradation of energy during a process. For example, a high temperature energy source can be converted to work. So, they are called as high quality than the same amount of energy at low temperature. For example, if 10 kilojoule of energy is available at 700 degree centigrade and 10 kilojoule of energy is available at 300 degree centigrade, then we say that the quality of energy at higher temperature, that is 700 degree centigrade, is more the quality of energy is more when the temperature is high. Another important aspect that second law provides a theoretical limit or thermal bottleneck. So, by introducing a term efficiency, second law says that a system has certain bottleneck or some thermal potential at which beyond which it cannot convert it the form of energies. So, we will come back to those points when we introduce the term efficiency. Another important aspect is that directionality of a process is quantified by a thermodynamic property what is known as entropy. So, we will give more emphasis on this entropy topic in the next lecture, and in addition that we also have another concept what we call as exergy, which is nothing but the maximum energy potential of any given source. So, these two topics will be addressed in my next lecture. So, let me start with the first thing that what we are going to talk about, the different two forms of energy interactions, that is work and heat, which is given from the first law. So, it has been said by first law, it has been said that work and heat, whether you call it as a work or heat does not matter to us, because they have same unit, they have same quantitative nature, whether they go out or come into a system, energy audit or energy balance has to take place. But next question is that why we have to say it is a work and why you have to say it is a heat. So, those things are addressed here. So, it is said that it is possible to convert work to heat directly and completely. So, we have given many examples on this aspect while dealing with the first law, but conversion of heat to mechanical work requires a special device which is known as heat engine. So, this means second law introduces a heat engine and how we are going to convert heat to mechanical work. So, in that way we can say that a concept of heat engine is introduced. So, what does this heat engine do? So, they receive heat from high temperature source, they convert part of heat to work, then remaining waste is sent to a low temperature sink, and so there is a cyclic device that occurs that involves the involving a working fluid that continuously absorbs heat from the source and rejects it to the surroundings. So, if you look at this particular figure, so it is a cyclic device. So, we call this as a heat engine. So, this this heat engine, what does it do? It takes a heat from high temperature source. So, it is a source. So, we call this as a in this things when we are talking about high temperature reservoir, we call this as a source, the word, and when you talk about low temperature reservoir, it called as a sink. So, the concept of source and sink is like a sea. If you add a drop of water into sea, its potential is such that its mass is changes negligibly. So, it is a so that means we can take out any quantity of water from a sea or ocean. So, we can say it is a water reservoir. A similar thing for a source we call is a high temperature reservoir, we say source, and same concept goes in a reverse way for the sink. Okay. And so, we say it is a source and it is a sink. So, the heat engine, what does it do? It takes, let us say, QH amount of heat and rejects QL amount of heat to the sink. Now, in the process what it does is we can get a work output. So, from heat, that means from a heating, by taking heat QH, it gives a net work output. So, this is how we say that, and we says that in doing so the heat engine must reject heat to the low temperature sinks, because of which, without which the work output is not possible. A typical example could be that we can have IC engines. So, this particular engine could be an IC engine, it could be a power plant. So, in a IC engine means we are giving energy in the form of fuel, but energies, there are some about 30% of energy goes out as a waste heat or to the atmosphere. So, that is a heat rejection. Similarly, for power plant, the heat comes from the coal, which is as a input, and it goes out to the through the condenser to the low temperature water or to the river. So, this heat engine could be anything, it could be a gas power plant, it could be ice engine or any other things. So, and in this process what happens, there is a working fluid which is involved. So, in a power plant the working fluid is steam or water, in ice engine the working fluid is the fuel and a mixture which is the charge, which we call this as a charge. So, in this process and in whatever we say we can get a power output in the form of shaft work for an ice engine, and we get also power output from a turbine in a power plant. So, in that way we call this as a net work output. Now, another concept that drops in is a refrigerator and heat pump. Now, we said that to get work output we have to take heat from the in a heat engine we have to take a heat from the high temperature source. Now, the question comes, is it possible that we can transfer heat from a low temperature reservoir or sink to and reject it to the source? Yes, first law says, a second law says it is possible, but in that case you will not get work output, you have to give work input to the to that machine. So, since it is a contradicting statement, so we do not call it as engine, because engine produces power output. So, instead of that we call this as a work consuming device. So, in a work consuming device we have two category, one is refrigerator, other is heat pump. So, now under what circumstances they will qualify whether we call this as a refrigerator or heat pump. So, for example, when you so that is a mostly decided is what is the desired effect. So, desired effect is nothing but what as user what do you want. So, if your requirement is at lower temperatures area or low temperature space, then we call this as a your desired effect is a refrigerating systems. Now, if your desired output is required for a high temperature source, then you can say it is a heat pump. So, in a refrigerator what does it do? So, here work input is given to a refrigerator. So, because of this we extract heat from a cold refrigerated space, and typically we call this as a low temperature sink, and we can reject QH amount of heat to the warm environment, and typically in this case is atmosphere, and obviously this TH is higher than the TL. So, in this process what happens? We take a heat from low temperature space and rejects to the high temperature zone, and through this process we are getting work output, and your desired effect is or your attention is concerned more towards this QL, and that is your net effect or your desired output or net desired effect. But in a other case, if your attention is focused that how much you are going to reject heat to a warm heat or heated space, then that means your attention is towards QH. So, in that case you call this as the work in this case we call this as a heat pump. So, these are the two basic distinction that we make in a refrigerator and heat pump. And of course, they here they also qualify that that they are cyclic devices and they are similar to heat engines, and here the working fluid is similar to the refrigerant, and we call this as a refrigerant. There the working fluid could be air, there could be fuel air charge, or it could be steam or water in a heat engine. And previously when you talk about heat engine, we introduced the term efficiency, which we say that the whatever work we get, we can that divided by the amount of heat that we supply will give you the efficiency. But in a refrigerator or heat pump, we define a indicator what we call as coefficient of performance, or in a short form we call this as a COP, and the COP is nothing but the desired effect by work input. So, desired effect could be heat from the low temperature sink or heat from the low temperature source. So, QL or QH, but denominator that is always work input W net, and the denominator by doing this energy balance W net nothing but QH minus QL. So, So, when you deal with the refrigerator, the COP is assigned, your desired effect is concentrated on QL. So, it is QL by QL minus QH. For heat pump, the desired effect is considered on QH. So, it is QH by QH minus QL. So, now by just simple addition of these two will tell you that the COP of heat pump is equal to COP of refrigerator plus 1. That means, COP of heat pump is always higher than a refrigerator. Now, having said this, now we will talk about two important statements of second law, and they are called as Kelvin-Planck statement or Clausius statement. This Kelvin-Planck statement pertains to a heat engine, whereas the Clausius statement pertains to a heat pump or refrigerator. So, what does this statement says? That this statement has to be taken as the way it has been reproduced. So, that is, it is impossible, and in fact these two statements are negative statement. So, negative statements means it is put in a negative sense. So, what does it mean? That it is impossible for any device that operates in a cycle to receive heat from a single reservoir and produce net amount of work. That means, we cannot construct a device which operates in a cyclic manner, but keep on producing work by interacting it with a single reservoir. For example, if you say it a heat engine, without rejecting heat to the low temperature sink, we cannot run a heat engine. So, for example, so when you have 10 kilowatt of energy that comes from high temperature source, and we are getting out 10 kilowatt of work as output, then it is not possible. It is not possible without, that means, because in this case QL is 0, although it is satisfies the first law, but QL is 0 means it violates the second law. So, that is what the form of Kelvin-Planck statement. So, no heat engine can have thermal efficiency of 100%. So, in a power generating device, that means in a power generating device, the working fluid must exchange heat with environment. That means, QL should not be 0. So, it has to have some number. Next is Clausius statement. So, this is based on it is also a negative statement, but it is based on refrigerator or heat pump. So, what does it say? It is impossible to construct a device that operates in a cycle and produces no effect other than the transfer of heat from low temperature body to a high temperature body. So, what does this mean? That for example, if you want to take a 5 kilojoule of heat from a cold refrigerator space and you are going to reject the same amount of heat by using a refrigerator, then without any work input you cannot do this. Although it satisfies the first law, but we have to go through, we have to give some work input. Okay. So, these are the two form of Kelvin-Planck statement and the two form of second law of thermodynamics. But this two concept has another role, and or many books call this as a perpetual motion machines, and which we call this a typically hypothetical device. That means, this point of time we have been telling that when both the first law and second law are satisfied, a process has to occur, and none of the processes have violated first law or second law. So, this particular hypothetical statement says that perpetual motion machine, which is never possible, and in thermodynamic sense we call this a perpetual motion machine, that if anything that violates the first law, which is called as a PMM, that is PMM 1, that means it can produce continuously work output, and any device that violates the second law, which called as a PMM 2. So, this particular typical concept which was introduced here, that in a first case we have we have drawn the schematic of a power plant, which says that this power plant is operated from the power which is developed from a generator and which is the net output power, and from that power we are continuously giving the input to the as a heat source. So, in this process what happens, we are basically we are creating energy. So, this is not true. So, that is so in that way we violates the first law of thermodynamics. So, in this same concept, when we are dealing with another similar concept, that we have a power plant which operates turbine and pump and boiler, but it takes QH amount of heat, but it produces work output, but there is no heat rejection. That means, it violates the Kelvin Planck statements. So, that we call this as a PMM2. Okay. So, these are the hypothetical machines. Now, we are going to introduce another important concept, what is a reversible and irreversible process or irreversibility. For example, we have been telling that a process when occurs in a very slow, that means we have introduced a term which is called a quasi-static process, which is the infinite slowness of that, which is the characteristics of a quasi-static process. Now, in a naturally occurring system, if some process occurs in a quasi-static manner, then we say quasi-static manner, then process occurs in one direction. But if same process can be reversed back to its original state, then we call it as a reversible process. So, two typical examples could be a simple pendulum which always moves, I mean since it is a frictionless pendulum, it has a some time period of rotation. And also another example could be quasi equilibrium expansion and compression in a piston cylinder device. So, that means this is nothing but a process which you can quantify. So, why do you require a reversible process? Because reversible process is mere idealization of actual process. So, in the second law, so the second law says that there is a second law says that there is a reversible process and there is a actual process. So, that what is the distinction between these two? So, what is the upper limit for that actual process can achieve? So, it can achieve up to some extent for its corresponding reversible process. So, that means it is a mere idealization of an actual process that occurs in a nature. So, it puts some theoretical limits. So, in the previously we have talked about heat engine and we have talked about refrigerator and heat pump, but we have to put some theoretical limit. So, what is a theoretical limit? So, to address those theoretical limit, the reversible process was introduced. Okay. Now, moving in that line, there is another concept called internal and external reversible process. So, a process is a totally reversible process, or we see when you say simple reversible process, when this process occurs, there is we have system as we have surroundings. So, so when you talk about the system, when you have this system and it occurs in a very slow process. So, in this slowness of through the slowness of process or quasi-static nature, we say it is a internally reversible process. Now, what happens at the same time, because of this occurring process, if the system outside the surroundings is not affected, that means there is no irreversibility due to the surroundings, then we say it is a total reversible process. For example, a total reversible process can be hypothetically stated that we have a thermal reservoir which is taking heat from a reservoir and that temperature is 20.00001 degree centigrade, infinite 0.1 degree centigrade. So, and the system itself is at 20 degree centigrade. So, what it does is mean that there will be a heat transfer because there is a very infinitesimally small temperature gradient in between. So, heat transfer takes place, but in a very it is occurring in such a slow process that as if nothing is going to be visible for system as well as its surroundings. So, we call this as a total reversible process. But in the other way we can view this particular concept is that we have a thermal reservoir which is at 30 degree centigrade, and but that from that reservoir we are taking heat to this piston cylinder device or gas, and that when that gas when that heat is going into this system or to the gas, the piston tries to move slowly. So, this slowness is within the gas and this piston. So, we call this as this process as internally reversible, but because of this there is some finite change in the surroundings. So, this particular process we call as internally reversible. That means, in this through this process we are not bothered what happens in the surroundings, and there are irreversibility that occurs in the surroundings. So, because of this reason we say it is an internal reversible process. So, these are the thermodynamic definition of a reversible process, and it introduced some irreversibility that is accounted due to friction, mixing, heat transfer between finite temperature difference, which is in this case chemical reactions. These are the some of the irreversible nature that introduces the behavior of a irreversible process. Now, having said reversible and irreversible process, we are now going to introduce the thermal bottleneck, or we say theoretical limit for a actual process, and that is done through a Carnot cycle or reversible Carnot cycle. What does this mean? Beginning we have introduced a heat engine. When we are talking about a heat engine, we say that certain quantity of heat is being taken from a high temperature source and some quantity of heat is rejected to low temperature sink, and by virtue of which we get a output. And whereas in a heat pump or refrigerator similar concept holds in, but there we are going to introduce work as a input to the system. Now, while this heat pump or heat engines or refrigerator they operate, what is the upper limit or what is the theoretical limit they can have? For example, as I mentioned that if the while transferring heat or work, at what temperatures they are sitting, that means at what temperatures that heat or work heat is available. To quantify this, we put some theoretical number, and that number is to be done through a reversible process, and this is introduced through Carnot cycle and reverse Carnot cycles. Carnot cycle refers to for a theoretical limit for a heat engine, reverse Carnot cycle puts a theoretical limit for refrigerator or heat pump. So, it was proposed by a French engineer Sadi Carnot in 1824. So, for a theoretical heat engine that operates in a Carnot cycle, they has composed of the following processes. They call it as a reversible isothermal expansion. The cycle that should have has a adiabatic reversible adiabatic expansion, reversible isothermal compression and reversible adiabatic compressions. So, he drawn that the cycles in a PV diagrams. What it sees that when you look at the process 1 to 2, it is a reversible isothermal expansion. When it goes from 2 to 3, it is a reversible adiabatic expansion, and 3 to 4 goes as a reversible isothermal compression, and 4 to 1 goes as a reversible adiabatic compression. So, in this process, when you say isothermal expansion, the temperature remains constant. So, it is called as a high temperature source, and when it rejects heats, it is treated as a low temperature sink. So, that means a heat engine operates between two limits, that means high temperature source and low temperature sink, and we know their temperature because their process is isothermal, and while doing this isothermal process it takes heat and from the source and rejects it to the sinks. So, for example, this process is such a slow process that here we are talking about adding heat to a system, but still we are keeping the temperature as a constant. So, although it is a very slow process, that means it is a infinite slow process. So, similar diagrams you can draw in a temperature entropy diagrams. So, there the process the 1, 2, 3, 4 process it is a rectangular in nature. Now, similar thing we can reverse it. So, we call this as a reversed Carnot cycle, or we call this as a Carnot refrigeration cycles. So, in that way the process goes from 1 to 2, 2 to 3 and 3 to 4 and 4 to 1, but the difference that goes here, that here heat is added in the process 2 to 3 and heat is rejected in the process 4 to 1. So, this is the basic difference between the heat in Carnot cycle and reverse Carnot cycle. And what are the important consequences that the Carnot cycle gives us? There are two important inferences, and it talks about the concept of thermal efficiency of a reversible and irreversible heat engine. The efficiency of an irreversible heat engine or actual heat engine is always less than the efficiency of a reversible one operating between the same reservoir. The efficiency of all reversible heat engines operating between the same two reservoirs are same. And also there is another significant concept that introduces a temperature scale which is independent of working fluid of substance. So, beginning when you talk about centigrade or Fahrenheit scale, it depends on the working fluid in the thermometer, but here the Kelvin scale does not depend on the properties of working substance. So, introduce a Kelvin scale temperature scale, and based on this temperature scale the theoretical limits of heat engines and refrigerators are defined, and we call them as a Carnot efficiency or Carnot COP. And similarly for refrigerator and heat pump, we call this as a Carnot COP for refrigerator or heat pump. Now, how do you find this Carnot efficiency? So, one important thing that I have been telling, that when you deal with a first thing we dealt with a heat engine first. In that heat engine we just take the introduce the heat, that is QH, W and QL. Now, apart from this we are also introducing the concept of TH of high temperature source and TL, that is low temperature sink. And from this Carnot cycle, when they introduce a Kelvin scale for a reversible process, a important relations that was developed, that ratio of QL by QH is equal to TL by TH. So, it is a linear relations, and this linear relations is applicable when the temperatures are expressed in the Kelvin scale, only in the Kelvin scale. So, that is the reason the advantage of Kelvin scale, because for a reversible process we can relate Q and heat and temperature in a linear fashion. By doing so, and for a reversible process, if you introduce the Carnot efficiency for reversible efficiencies for heat engine and refrigerator are defined. So, for a Carnot efficiency we can define as, instead of QL by QH we are going to put as TL by TH. So, we call this as a Carnot efficiency. So, for a heat engine there are two efficiency, one is the actual heat engine efficiency, other is the Carnot efficiency. Similarly, for refrigerators we have the Carnot COP for refrigerator, where the Q temperatures are replaced with TL, the heat terms are replaced with TL and TH. Similarly, for heat pump, we can say COP for heat pump is equal to TH by TH minus TL. So, now having said this, we have two important conclusions, one for heat engine, other for refrigerator. So, the efficiency of an actual engine is equal to a reversible engine when it is a reversible engine, both the efficiencies are equal, and for irreversible engine it is always less than the Carnot, always less than the reversible heat engine efficiency or Carnot efficiency, but any efficiency of any actual engine, if it is greater than a reversible value, then it is such an heat engine is impossible. And similar logic is also true, that actual refrigerator efficiency is always less than the COP value of COP of irreversible refrigerator is always less than its reversible value. So, similar logic can also be framed for heat pump. And finally, when you are going to conclude from this from Carnot cycle and reversible Carnot cycle, following statements can be made. First, when we are talking about efficiency, it is a thermal performance indicator that shows that energy has a quality as well as the quantity. Higher value of efficiency implies that more of higher thermal energy can be converted to work. So, higher is the temperature, higher is the quality of energy. Second important conclusion can be derived that thermal efficiency of actual engines can be maximized. That means, we can for any actual heat engine, if you want to maximize the efficiency, that means we can go up to the Carnot efficiency to how, by supplying heat to the engine at highest possible temperature TH. That means, if you want to increase the efficiency, Carnot efficiency, either we have to increase TH or reduce TL. So, that efficiency will be more and more. Similarly, for COP also we can have similar logic, that COP of for both heat pump and refrigerator decreases as TL decreases, and that means it requires more work to absorb heat from low temperature media. As the temperature of refrigerator space approaches 0, that means, if when your TL goes to 0, this means the amount of work required to produce a finite refrigeration approaches to infinity. That means, COP of refrigerator goes to 0. Okay. So, with this I complete for today's lecture. So, at the end of these things we will talk about some simple numerical problems. As far as this numerical problems for this section is considered, is just an arithmetic addition, subtraction, multiplication, and the problems are very simple because the relations are also very linear. So, the first problem that we are going to talk about, an engine produces a power output 40 kilowatt with thermal efficiency of 25%. Calculate the fuel consumption rate. So, we are given with fuel calorific value of 40 megajoule per kg. So, the solution that we can say here, that we the calorific value we can recognize as QCV, and that is 42 megajoule per kg, and we say efficiency as 25% or that is equal to 0.25. So, this efficiency can be written as W net by Q in, and that is nothing but 0.25. So, we have W net is already given 45 kilowatt. So, from this we can get Q in as 45 by 0.25, 180 kilojoule per second. Okay. So, we get Q in. Now, we know calorific value, but we require fuel consumption rate. So, fuel consumption rate can be quantified as m dot is equal to Q in by QCV. So, Q in is 180 kilojoule per second by QCV is 45 megajoule, 42 megajoule, that means 42,000 kilojoule per kg. So, if you divide that, we get m dot as 0.0043 kg per second, or it can be converted to kg per hour, that is 15.4 kg per hour. So, this is very simple process, simple. W net by Q in is nothing but your efficiency. Next problem is deal with the heat pump. So, heat pump is used to maintain the temperature of a house at 25 degree centigrade, whereas outside temperature is minus 2 degree centigrade. So, for example, here the solution, for the solution what you have to do, that we have to simply create a schematic diagram of a heat pump. So, we are talking about a heat pump HP, and it must reject QH of heat and takes QL of heat, and it must consume CW in. Okay. So this we can say is a house, and this is what we can say ambient. So, ambient is at minus 2 degree centigrades. So, here when you have given you temperature, you must convert it to Kelvin. So, this would be minus 2 degree centigrade, and here it is 25 degree centigrade. So, here we are not going to talk about the temperature because it is a simple heat pump, and we are not talking about the reversible nature of the heat pump. So, temperature has no role, but although it is given in this problem. So, we will start with, so what does it say? It rejects heat at a rate 70 megajoule per hour. So, that means heat is rejected from this house at the rate 70 megajoule per hour. So, this should be same as that of QH. So, first thing we can start with the basic definition. COP of heat pump, that is QH by W net, and that is nothing but 2.5. So, from this we can get W net, which is power consumed, that is 70,000 kilojoule per hour divided by 2.5. So, W net would be about 28,000 kilojoule per hour, or you can say 28 megajoule per hour. And then you have to find out what is QL. So, QL is nothing but QH minus W net. So, this is 42 megajoule per hour. So, here we have not given any kind of reversible nature. So, the temperature has no role in solving the problems. But the next problem we will talk about a Carnot heat engine where temperature will have some significance. So, here this Carnot heat engine, for this Carnot heat engine we have to also draw a similar schematic diagram. Okay. So, here it is a heat engine. So, we have a high temperature source, so heat is coming from high temperature source TH, and source temperature is 700 degree centigrade or plus 273. So, it is 973 Kelvin. So, TH is equal to 700 plus 273 973 Kelvin. Similarly, TL is 30 degree centigrade, that is 30 plus 273 303 Kelvin. So, this is these two conversion is a must. So, TL, that is sink, we can say 303 Kelvin. So, heat is taken QH, rejected as QL, work output is W out. What is asked? What is the thermal efficiency of the heat engine? So, we say it is a Carnot heat engine. So, first thing we can say Carnot efficiency we can find out, since it is a reversible heat engine, that is 1 minus TL by TH. By putting this number, we get 0.688. So, efficiency of this engine is 0.688. That means, this particular engine cannot have efficiency more than 68.8%. That is the upper limit. So, we say upper limit for this engine is 68.8%. And when this engine operates in this limit, we are supposed to ask what is the heat rejected to the sink. So, heat rejected QL, we can write the relations, because since the process is reversible, we can have this ratio QL by QH is equal to TL by TH. So, that is 303 divided by 973. So, QH is 500 kilojoule. So, from this we can find out QL as 303 by 973 into 500. So, QL is found to be 155 kilojoule. So, this QL answer we can say 155 kilojoule. W net is QH minus QL, that is 500 minus 155. So, it is 345 kilojoule per kilojoule. So, we have W net, we have QL. Okay. So, these are some simple problems. With this I conclude my lecture for today. Thank you for your attention.